screen mode. There you go. All good.
Okay. Very good. So thanks, Manas. And as Manas said, this is a joint presentation between Manas and I, where we'll be discussing how modeling with SysML v2 can enable the digital thread. So let me go back here. So I'll start by giving the presentation, and Manas will finish with a short demo. I'll start with some MBSE background where I'll talk about the role of the digital thread in the context of system engineering and MBSE more generally, and then get into this more specifically how SysML v2 can help enable that digital thread. So starting with this value statement that's comes from the NCOSE System Engineering Vision 2035, talks about the purpose of system engineering, that it aims to ensure the pieces work together to achieve the objectives of the whole. That's what we do in system engineering. And one of the key practices in system engineering is architecting balanced solutions that satisfy diverse stakeholder needs. So we're architecting solutions, balanced solutions that cross these different pieces of the system, and inherently requires us to basically connect data that spans the various technical domains and disciplines. So it's really foundational to system engineering, whether it's electrical, mechanical, software, controls, reliability, safety, all these different disciplines, the technical domains typically being centered around the subsystems themselves, like power and control and the like. So this is basically this notion of a, if you will, a digital thread and connecting data is just foundational to the practice of system engineering. Now, our practice, as we all recognize, typical V process where we flow requirements down from mission to system to subsystem to components. And then we integrate and verify going back up. And architecting is applied at each level, starting at the mission or system of systems level, where you architect, across systems. And then you architect your system to specify the subsystems, and you architect your subsystems to specify your components, et cetera, et cetera. So it's a recursive process that applies up and down the V. If you look at the traditional system engineering process, which I grew up with, we used very informal techniques for architecting systems. A typical system block diagram was pretty much a key artifact of system engineering, one of many, along with ICDs and CONOPS and many other artifacts. But if you look at this block diagram, which I pulled off the web, it's for an LCD TV system block diagram. The person who created it, probably the architect on this program, he understands the domain very, very well. There's no question about that. But although this represents implicit good domain content, it's very imprecise. And so it's very difficult to distinguish the component hierarchy, or, for example, interfaces. They're very extreme. They're really not even specified here. They're just indicated, if you will. You can't really tell the difference between functions and components, or between successions or sequences and connections. So there's a lot of good implicit content in here, but again, it's very imprecise. The other aspect is that it's a standalone artifact. It's disconnected from other system data. And this basically what I grew up with. This was the kind of system engineering that we ended up having to do. And so when it comes to, for example, a change in requirements, there's no way to directly relate that change in requirement to a change in something on this block diagram, or a change on this block diagram and how that would ripple to detailed design or to analysis or to test. So, or to other views of this system. So that's really how we been doing system engineering traditionally for many years. It's important to remember that. And we've made a lot of progress with MBSE. We've gone beyond this in many cases, but we're still, we still have some significant limitations. So when we look to the future of system engineering, you look at, again, referring back to the Nkosi SE vision, the future of system engineering is model-based. And model-based or system engineering, MBSE, is kind of a natural part of this digital transformation that's spanning virtually all enterprises and up and down the enterprise. And the intent of the digital transformation is to capture your data as digital artifacts, but more importantly, to integrate them semantically. So the data turns into information. And then you can protect that data, you can operate on that data, you can automate things like workflows, things that Craig was talking about earlier in terms of his trends. A lot of things that can happen once you move to this digital form. And MBSE is really just an incarnation of that. Now, as we look to the future, clearly, MBSE will be leveraging technologies such as AI and many others. Clearly, that will be important, but equally as important, perhaps more important, is sort of maturing our practice, making it a broader adoption, and applying MBSE to a much broader scope. So currently, MBSE is often applied still really more towards the front end of a program, not always, but often. Whereas as we move forward, we want to see MBSE applied across that full life cycle through design and development and out into production and then out into sustainment. Basically, that concept of a digital twin from early concept all the way out through sustainment. And in addition, we want to see the scope expanded so that model-based system engineering is applied from system level all the way down to component level. Again, many examples where that's done today, but we want to see this become standard practice where it's applied across the life cycle and up and down the various levels of system design. Clearly, part of the future is to do a better job of leveraging patterns and reference architectures. This will be really, a key aspect of reuse and reducing cycle time and all the good things that come with this kind of practice. Very importantly, though, is integrating our MBSE approach into Agile system development processes. And when I use that term here, I mean it in the sense of Agile processes that support automated workflows. And as part of that, configuration management of the digital thread. So this is configuration management of this system model, this model of our system, and all of the artifacts that it relates to that span the life cycle of system development. So this goes into detailed design and analysis and test and ultimately to manufacturing and sustainment. So we need that connectivity and we need to manage those connections across the full life cycle of development and support these automated workflows. That's how we'll get Agile at a systems level. And if we do this, we improve our system engineering and we get all the kinds of things that system engineering has always tried to do, which is manage complexity and risk and being responsive to changes and requirements in design and supporting reuse and ability to reason about our systems, establishing that common understanding and enabling automated documentation and reporting and all those kind of things. So we want to, we're doing this to just basically improve our system engineering. I referred to Agile process. I mean, the real key here for an Agile MBSE process is that you verify your system in a model before you build it. I mean, that's really what we're trying to do. And this is an incremental process. You don't just model your whole system all at one shot. here it is, start, and here's the whole system model. So it's a very incremental process, but this incremental process involves specifying, designing, and verifying the system as you move down the V and back up the V in a virtual sense. And you do this before you build. And again, emphasizing that in order to do this incremental process, as you're making these changes, and there's detailed design artifacts, there's verification artifacts, there's analysis, all of these different artifacts are must be maintained in sync as you move through this process. So the management of the connected data must be seamless. That's where we have to get to. This is one really hard job, but I think technologies such as Syndeia are the kinds of technologies that are essential to help do this. So I kind of lay out a challenge here for MBSE, basically to enable digital threads by providing seamless access to the system model. That's not good enough. The system model has to be a high quality, and it has to be current. It has to be up to date, and the data that gets connected and presented to the DE stakeholders has to be in the right form. So we have to do all of these things in order to really achieve this overall objective. So producing, high quality system design specs that are complete, consistent, verifiable, and traceable. I mean, that's really what we need to do in MBSE, and that's a hard job. We need modeling practices that support rapid design iterations throughout the life cycle. We need to provide views of the system model that support different stakeholder viewpoints, including those of the design team, the software, mechanical, electrical. We got to present the data in a form that's useful to them. And of course, we have to provide that access, that seamless access and configuration control of the system design data. I'm using that term synonymous with system model. Now, this isn't accomplished by the language alone, clearly. This must be addressed by the language, by the tools, the practices, and the skill base, and basically the culture of system engineering. So this is a really huge challenge. And SysML v2 can contribute to helping to address this challenge, but obviously you need a lot more than language. But in this next section, I'll give you an overview of SysML v2, and I'll try and bring out some of the ways in which it's helping to address this challenge. So let's start with the objectives and approach. And we're really, our goal really was to substantially improve MBSE with SysML over what we had with SysML v1 and help us achieve that future vision of system engineering as being model-based, to really help make that happen. And so in order to do that, the goals were around improving the precision of the language, making it less ambiguous relative to v1, to making it much more expressive, to address new concepts such as variant modeling concepts, to ensure its consistency and regularity across the language, to ensure that the language is more usable. And part of this comes from the kind of this more regular patterns of use, to make it more extensible to domain-specific applications, and to make it more interoperable. So these were all the things that we're trying to achieve with the language, and I think, in fact, we're achieving. Time will tell how well we achieve these. So the approach that we took was to introduce a new meta model that is no longer constrained by UML. So SysML v1 was constrained by UML. UML, of course, was designed for software modeling. So in this new meta model, we preserve many of the UML modeling capabilities, but we put the focus on system modeling. And this new meta model is grounded in formal semantics from the beginning, which we didn't have with UML. A second key element is a more flexible visualization with a flexible view and viewpoint mechanism, and it's supported by both graphical and textual syntax. I'll show you an example of that in a moment. And then the third key element is the notion of a standardized API to access the model from external models and tools, and say a bit more about that. So let's start by just taking a look at the SysML v2 language architecture. And what you see here is SysML sits at the top of a stack, and below it is a foundation, is another language called KerML, or a kernel modeling language. And KerML has 3 layers that you can see here. At the lowest layer, it has what's called the root syntax layer, where you have really foundational concepts such as element, relationship, namespace, annotation, and basic concepts like that. And then at the next layer up, the core syntax layer, you introduce the core semantics of the language. And the semantics are based on first-order logic. And it basically provides the semantics of classification, of classifying things and giving meaning to things by identifying what their features are. And there are core concepts in this layer, such as classifier and feature and generalization and others. Then the next layer up is the kernel syntax layer, which adds basic capabilities over and above what you get in the core syntax that are needed for modeling languages in general. And so, for example, it introduces the concepts of structure and behavior. When you finally get up to the SysML layer, this is the domain-specific language, if you will, built on top of KerML. This is where you introduce concepts that we use in systems modeling, such as requirements and activities and states and parts and items and constraints, things of that sort. So this is how the language is architected. And it, in fact, will enable other domain-specific language to be built on top of KerML and SysML, and integrated in as we go to the future. And that will also be important, very important for the digital thread, is to have, common languages that are based on a common foundation. So the base capabilities of SysML v2 are shown here. So you see structure and behavior on the left, and those look like SysML v1 structure and behavior, and they are at some level. But they're much more integrated. They're much more precise. They're much more regular, more powerful things you can do with that capability than what we had in V1. We have requirements. I'll say a few more words about requirements, but they're also more precise in that you can represent not only a text requirement, but you can represent requirements in terms of constraint expressions. I'll show you that in a couple of slides. We have, instead of parametrics, we have analysis cases. And analysis cases are really kind of a nice way to specify an analysis that can then be solved by other solvers. So you can integrate the system model with analysis models, I think, more effectively. And the analysis cases are supported by a very comprehensive expression language that allows you to state qualitative and logical and quantitative expressions in this expression language, which of course we didn't have in V1. And verification, again, are more robust. We have verification cases as opposed to test cases in SysML v1. And then in view and viewpoint, we have this flexible mechanism for defining user-defined views over and above our standard views. So this is the sort of a base capability of V2. If you look a little bit under the hood and you go to the SysML v2 specification and clause 7, this is the outline for what's covered in there and kind of gives you a sense of the scope of the concepts that are part of SysML v2. I won't go through all these, but you can just take a quick look and you'll see the kind of the scope of the concepts. I want to start here by introducing this definition and usage pattern. It's something that was originally introduced in SysML v1. We use the term definition and usage. We referred to a block, for example, as a definition element. You defined a block, And then you would have a SysML v1 and you would have a part, and that part would be typed by the block. And the idea was you define the block once, but you can have many different parts that are used in different contexts, but all with the same type. So you define something once and you use it many times. So that is a really powerful concept, reuse concept. And it was applied in SysML v1, but not in a very regular way. So for example, we did refer to activities as definition elements and actions as usage elements, but it was a very different relationship between actions and activities versus parts and blocks, or similarly with other concepts in the language. In SysML v2, the concept of definition and usage was built in from the ground floor. So it's foundational to the language. And so virtually all concepts in SysML v2 have a definition and a usage construct. And so again, you can define things once and use them many times. A really important reuse concept. And this pattern is applied very consistently throughout the language, really helps with usability and with automation and other aspects. Just to highlight that, you see on the right some of the SysML v1 concepts and the corresponding v2 concepts on the left. And so, for example, we have part, property, and block and SysML v1 on the right, and on the left, you can see part and part def. So this is the corresponding concepts between the v1 concepts. They're similar in nature, but you see this terminology, part and part def. This is the definition element, part is the usage element. And then if you go down here, for example, proxy port and interface block, you see port and port def, or action and action def, or requirement and requirement def. So they all follow this very common terminology, but more importantly, they follow a common pattern. So they're not as idiosyncratic as it was in SysML v1. Everything's very regular. And furthermore, this pattern of definition and usage is very, very powerful. It enables you to decompose virtually anything, whether it's parts or ports or actions or requirements. You can decompose and you can specialize everything. And this gives you a tremendous amount of flexibility in the language and also makes it easier to learn and to use. Now, it's not a simple language. I don't want to kid you and say it's simple. It's not. There's a lot to it. But I do anticipate that people will be able to come up to speed on at least a sort of a foundational part of it fairly quickly. And once you understand this basic definition and usage pattern, you're coming a long ways towards understanding the language and what it can do. So let's look at a simple example here. I'm going to show you first in the textual syntax, and I'll show you the graphical syntax that corresponds to this. So SysML v1, of course, did not have a textual syntax. SysML v2 does. So here we have a part vehicle, and it has an attribute mass that's equal to the engine's mass plus the transmission mass. Right off the bat, you're looking at an expression. In SysML v1, some of the tools provided some kind of expression language, but it wasn't a standard part of the language. This is a standard part of the language. It's parsable, it's meaningful. So engine.mass is, in fact, the mass of the engine that can be evaluated. Similarly with transmission.mass. It performs an action called provide power. It has two parts, engine and transmission, obviously many other parts, but in this simple example, engine and transmission. Both of them each have an attribute mass. They each have a port. The engine port is called torque out port. The transmission is torque in port. And they both perform actions. The engine performs generate torque. The transmission performs amplify torque. You can see a connect statement where these two ports are connected. So engine.torqueout port is connected to transmission.torquein port, transmission.torquein port. And you see the provide power actually is referencing this provide power down here. So here I've defined my behavior, if you will, very simple behavior, as this provide power with two nested actions, generate torque and amplify torque. And that's where you see that the engine is referencing provide power dot generate torque, this, and transmission is referencing provide power dot amplify torque, or this. So we're cross-connecting the structure and the behavior in a very precise and straightforward way. If you look at it graphically, you have a part here, vehicle, with the mass equal to the engine's mass and plus the transmission mass, this. You see the connection here. It's not named, but this connection can have a name, but in this case, there's no name. So, but it does show connecting the engine's torque output to the transmission torque input. You see that it has two parts, the engine and the transmission, but the details aren't shown. You see that it performs an action called provide power. And this provide power is what's called reference subsetting. Don't worry about that, but that's a symbol for it. It's actually referring to this provide power. And so you get a sense of the fact that the graphical representation is just a different rendering from the textual representation. They're two renderings of the same underlying model. Now I can also show different views. Like in this case, this is an interconnection view of the vehicle with the engine transmission connected to their ports. You can see that's a subset of what's here in the model. Or I can show a action decomposition, provide power, generate torque, amplify torque. That's showing this, and many other views. So this is what you have is this textual syntax, this graphical rendering, the ability to render this information in different ways to support different needs. I'll just bring out one additional concept. Just it's limited time here, so we don't have time to go through all the different concepts in the language, but just to highlight a SysML v2 requirement. So in SysML v1, we had was really good introduction of the concept of a requirement. We actually hadn't had that in models before, at least that I'm aware of. And the idea was you could bring your requirements into the model and then show traceability to other parts of your model, your design, your test cases and analysis, et cetera. And really a great idea to do that. But in V2, we had a textual description, a shall statement for a requirement. Later on, we did introduce what was called a property-based requirement, still a bit cumbersome to use, but the idea was brought into SysML v2 as part of any requirement. And the idea is that in addition to a shall statement like this mass requirement, the vehicle mass shall be less than the required vehicle mass. In addition to that, we have the ability to express it as a constraint expression. So here you see mass actual is less than or equal to mass required. This is a constraint that can be evaluated as true or false or pass fail. So this capability here to bring in constraint expressions into any requirement, you may in fact for most of your requirements still just represent them with text, but you may choose for critical requirements to actually express them in a more formal way such that they can be evaluated. So for example, if I did the analysis and I did a roll-up of my mass, I could compare it to my required mass, which in this case is 1,650 kilograms. I can do the comparison and you can evaluate whether you pass this requirement or not. It also includes the ability to include assumptions, like in this case, this requirement will only be valid if the fluid mass is less than 40 kilograms, less than or equal to 40 kilograms. So these are the kinds of things that get introduced into SysML v2 that are just really powerful. So I'll just leave it at that. So many other concepts in SysML v2 that provide, a lot of expressiveness, very precise, and just, enable you to say what you want about your system and develop those specifications in more complete and precise, consistent and traceable ways. So one of the things we talked about, I mentioned before, was the Agile process. So really critical to having an agile process and the way in which SysML v2 can support that. Well, it will be dependent on, to some degree, on the methodology that you use. But SysML v2 does enable you to use certain kinds of methodologies that could support very rapid design and iteration. And the principle is to decouple your system model and yet into various pieces and yet keep them integrated. So you want them both decoupled so individuals can work on them in a team environment without stepping on each other, but at the same time, keep those pieces that they're working on integrated. So for example, there may be different people working on different subsystems that are developing the models for different subsystems. And you want those to be worked on concurrently, but not to be stepping on each other, etc. So the idea here is that you have, system does system architecting and specifies subsystem specifications. Subsystems, let's say, does subsystem architecting and specifies component specifications. So the idea is to use a black box specification in the model as kind of a stub for the design model. So the black box specification that comes out of the system, the black box specification for the subsystems, for each subsystem, is a stub for designing that subsystem. And similarly, what comes out of the subsystems are sort of black box specifications for the components that are stubs for the next lower level of design. So you architect these subsystems, and each subsystem is a specification that gets architected for the next level, and you flow down that way. And furthermore, the other key part is the ability to integrate the lower level designs back into the higher level subsystems and continuing that back up to V. So there are patterns, and we're exploring these right now and really trying to get them defined. They're not simple. It's going to take some rigor and discipline to apply. I mean, there's just no getting around it. This is a complex process. But I think with some light level of automation, we can get this process so that it can be done in a reasonably straightforward manner and scale with complex systems. That's still to be determined, but I'm very encouraged that we can get there. And that will require all of the users to really dig in and learn this, and not just learn the language, but learn the patterns of how to use the language. So that will be really important going forward. So if you look at the system model and you take advantage of the different views that we have various standard views. And again, you can define user-defined views that you customize for your own purposes and for your own stakeholders. But we can have multiple views of the system. So for example, this one, let me try this and go to an expand mode here. So here we see the mass requirement that I was referring to before that has the constraint expression in it. So here it's part of the vehicle spec, and of course there'd be many requirements part of the vehicle spec. And we often may or may not show it graphically. We may choose to show it in tables like we've done with V1, but there are cases where you show it graphically, but this could equally be a table. And then let me try this. Here we're showing this mass requirement allocated to the vehicle. And so here's the dry mass of the vehicle. And you can see the vehicle has a bunch of other features. And let's just look at, for example, the vehicle states. And if I do this right, you can see that, let's just say I double-clicked on the vehicle states, and up pops a view of the state-based behavior of the system. In this case, very simple, off and on states. And you can see that there's some transitions here from off to on, which occurs when you get this ignition command and it's equal to on. Then you send a start signal to the controller and you transition to the on state. This is part of the expression language. When you get in the on state, you perform a self-test on entry, you do provide power, and you apply the parking brake before you exit. You assert there's a constraint here that the electrical power must be less than or equal to 500 watts. And then there's similar transition from on to off with the ignition command equals off. So there you see an example. Now, if I go over here to the right, it says provide power. Well, you might have here's the provide power action with the engine generating torque and the transmission amplifying torque. So you see elaboration of the action. If I go to back here and I want to look at, say, the parts here. So I can go up here and I can see the parts tree. So you can see the parts, the engine, the transmission. The engine has 6 cylinders, etc. If I want to see how these are interconnected, I can look at a interconnection view. And then if I want to look at one more view here, I want to see how this mass test is verified. I can show this mass verification case. And of course, you could see this graphically as well. But this is showing that you weigh the vehicle, you evaluate pass-fail, that this is the kind of verification case is it's a test case. The document objective, et cetera, et cetera. So the point is that when you create this system model, you contrast this with the block diagram that I showed you up front. You can start to see the power of a system model. And it's the digital thread starts here. It doesn't end here, it starts here. Because what we want to do is take this really rich data set about our system and provide the information to the other designers and other stakeholders, the data that they need in the form they want it. So that may be in some particular view to selected stakeholders, and make sure it's completely connected and integrated, and that we had the ability to develop this model in this agile way, incrementally as we move through this design process, moving down and up the V. So, any rate, that's the idea. So we've got this data set, the system model, in a repository. Now the question is, how do we connect? Well, SysML v2 introduced this API. This API is a wrapper around the repository that allows other external applications and tools to access this data and do all kinds of things with it. So during the development of SysML v2, we had a reference implementation, and we did proof of concepts where different external applications would begin to start to interface to this repository, several of which were using the API, and others, are going to use the API. And I'll just illustrate 4 cases here. So first is this CAD viewer. This is actually a quadcopter with 4 rotors and a sensor looking forward and field of view. This geometry was actually incorporated into the SysML v2 model. The v2 model is probably not for, still needs some work to make it a bit more usable, but it has really powerful capability to represent basic geometry, such as like this field of view or the basic physical layout of the system at a very high level, not intended to be a CAD model, but intended to integrate with the CAD model. We also had a proof of concept where a solver called Maple very powerful analytical solver, captured equations in the analysis cases in SysML v2 and then extracted them and solved the equations. Of course, we did this with v1, but again, I believe this ability to have analysis cases with the expression language is a huge step forward to integrate with analysis. We had one of the visualization tools, Tom Sawyer, use the API to extract data from the model and then create graph visualizations of it. Manas will also show an example of that. But you can do all kinds of things on the visualization side. We're not even restricted to 2D anymore. We can go to 3D visualization. I'm hoping the tool vendors pick that up and give us 3D graph representations. I really hope they pick that up because I personally think it's going to give new insights into this data. And then the fourth, of course, Manos will be talking about, but it was Syndeia, where he pulls data out as the model gets updated in the form of change sets or commits. And then that's what these orange dots represent, different change sets, commits. And then he relates those to other commits and other tools. And this is where the digital thread gets established and maintained and managed. So all of this is the kind of capability that we're getting to hopefully enable this digital thread. So let's go back to the initial challenge and just ask ourselves, how does SysML v2 address the challenge to enable digital threads, providing seamless access to the system model, and the system model is high quality and current and in the right form. So the first challenge was produce design specs that are complete, consistent, verifiable, and traceable. Well, hopefully you begin to see that this is a robust system modeling language. It's precise, it's expressive, it has the potential to do this. It's not free. You've got to do a lot of hard work and be good systems engineers to do this job right. But if we do it right, we can achieve this goal here. Use modeling practices that support rapid design iteration throughout the life cycle. Well, that is, I was introducing these patterns for going up and down the V, this decoupled plus integrated, to support basically concurrent engineering, so different team members can work concurrently on their part of the model and then still integrate into the whole. And I believe, again, that will have to be time tested. But I believe we have that capability in v2. To provide views of this model that support different stakeholder viewpoints, well, we do have a very flexible view and viewpoint mechanism, along with the standard views, which may be adequate for many uses, but you can go well beyond the standard views. Create tabular views unique to a electrical designer or whatever it is that you feel you need. And providing seamless access and configuration control. That, of course, is a standardized API. So this is how SysML v2 plays its part in enabling this digital thread. So I'll just reiterate that the future of system engineering is model-based. We must move to model-based. There isn't not really an alternative that I can see. And that's clearly what the SE Vision 2035 states. And I think that's a relatively shared view. So can SysML v2 help achieve that vision? I think it can. Can't do it by itself. It needs tools. It needs good practices that need to be developed. It needs a real mature workforce that really is made of good system engineers with good system modelers that take time to learn both the language and the practices. And if we do that, we can achieve the things that we talked about. So our plan forward is to basically With respect to the SysML v2 specifications, we're planning to submit the specifications for final adoption and submit them to the OMG for final adoption in December of this year. It is possible and maybe even likely that it will move out 1 quarter, but no more than that. So it could move out to March of 2025. Meanwhile, the tool vendors are actively developing their tools and implementing these specifications. And that's going on, and hopefully you'll start, well, Syndeia, for one, has already done that, but other tool vendors, authoring tools and the like, are aggressively working on their implementations. And we'll continue to evolve these practices for V2, modeling with V2. We'll take advantage of the fact that we have this OMG system modeling community. And if you don't know, go to the website, OMG website, and see if you can participate in that. And the other thing that we're really encouraging is that organizations and practitioners, that they initiate their transition planning. This is really important. This is a big step. It's not just a new version of a tool. It's a new language with new practices, new training, but it's exciting. So jump in, take advantage, jump in now. There's some excellent material on how to transition, some guidance that was prepared out of the Department of Defense, the Digital Engineering Modeling and Simulation Office under Daniel Hedema. And there's a wiki that's on our MBSE wiki that's shown right here that has a lot of that guidance that was developed as part of that project. So we have I'll finish up by just noting that we have a public repository for SysML v2. It's part of the original repository that was set up as part of the SysML v2 submission team. This says 2024-05. We're actually up to 2024-07, so slide's a little off. Lots of content, including training material, and the pilot implementations are there. You can access those in a couple of different environments. Talk to Manas about that if you're interested. And there's an open source repository, and there's a Google group that's becoming quite active. A lot of folks on it. They ask questions and try and provide answers. And so you can go to this Google group and the like. So with that, I'm going to wrap up. I'm going to turn it over to Manas, and he's going to do a short demo. Manas, I don't know if you want to leave time for questions now or do it after your demo. I'll defer to you on that. So thank you.
I think we'll do it. We'll do it after the demo, Sandy. It'll take like maybe 20 minutes or so. And then before we get to the break, we'll pause for demo. It also gives you some rest from speaking for the last 45 minutes. Thanks a lot for that excellent presentation on SysML v2. Sandy, you couldn't have said it better, that it is the future of model-based system engineering. And I'm going to talk about that. It's going to have a big impact outside MBSE. It's not just MBSE, but big impact outside. So let me see if I can share my screen.